Kita bosa science, kwano kwa beti science, rafu ya bosa science, truth na beta, truth na omega, truth na alpha science.
The Science Foundation College enamave ku Lwejjinja ng'oyingira kilomita emu. Ssomero lya Dene Boarding eri abawala n'abalenzi. Ku O-level tusomesa arts ne sciences ate A-level tusomesa sciences zokka. Omwana mulete ku The Science Foundation College. Ffe tusinga okusomesa sciences. Okumanya ebisingawo kuba ku 0753 8 27 09. The Science Foundation College, based on sciences and based for sciences.
Dr. Bosa is a teacher at the Science Foundation College, the best school that teaches sciences. At A level, we teach sciences only. At O level, we teach arts and sciences. Today, we are going to study atomic structure. Before we look at the structure of an atom, let us look at an element. An element is a substance that cannot be split into simpler substances. An atom is the smallest electrically neutral particle of an element that can take part into a chemical reaction. An atom is composed of protons, neutrons, electrons, whose properties are given in the table below. We have protons, the symbol small p, the charge is positive 1, the mass is unit. The neutron, the symbol small n, the charge is 0, the neutron have no charge, it has a mass equal to that one over proton. Electron, the symbol small e, the charge is negative, it has a mass which is 1 over 1,837 of that one of a proton. So compared to the proton, the mass of an electron is almost negligible. Atomic number is the number of protons in an atom. It is usually equal to the number of electrons. All atoms of the same element have got the same number of protons and electrons. Isotopes are atoms of the same elements with a different number of neutrons. We saw that all atoms of the same elements have got the same number of protons. So we can also define isotopes as atoms with the same number of protons but different number of neutrons. Atomic mass is the sum of protons and neutrons in an atom. Atomic theory states that an atom is composed of a nucleus containing protons and neutrons situated at the center of an atom and surrounded by a system of electrons. Electrons rotate around the nucleus in definite orbitals called energy levels or quantum shells, which are specified by numbers 1, 2, 3, or letters, capital letters K, L, M, N, dash, dash, beginning from the one nearest to the nucleus. The atomic theory says that an atom is composed of a nucleus in the center of an atom and is surrounded by a system of electrons. Electrons rotate around the nucleus in orbitals called energy levels or quantum shells. These orbitals are specified by numbers 1, 2, 3, 4, or letters, capital letters K, L, M, N, and so on, beginning from the one nearest the nucleus. The numbers 1, 2, 3, 4, or the letters K, L, M, N are called the principal quantum numbers. These are called the principal quantum numbers. Each energy level is associated with a definite amount of energy. The energy in each energy level will increase from K, L to M to N, and so on. From the nucleus, as the energy level keeps on piling, also the energy in each energy level keeps on increasing. An electron, to reside in a certain energy level, must have a definite energy. An electron to reside in a specific energy level should have a definite amount of energy. If extra energy is supplied to an electron in a given energy level, it jumps to energy level with higher energy and is said to be excited. For example, if this electron in principal quantum number 1 is supplied with energy, it may jump to energy level 2, where it is said to be excited. It can jump to energy level 2, energy level 3, energy level 4, depending on the amount of energy supplied. Because to reside in energy level 2, it must have a given amount of energy, or specified amount of energy. To reside in energy level 1, an electron must have a specified amount of energy. So any extra energy it absorbs, it can either jump to energy level 2 if the energy it has absorbed is enough to enable it to reside in energy level 2, or to energy level 3 if the amount of energy supplied is enough to make it reside in energy level 3. So an electron which has absorbed extra energy is said to be excited. If an electron falls from energy level with higher energy to an energy level with a lower energy, it emits the extra energy in the form of a radiation. The energy absorbed by an electron to jump from one energy level to the higher energy level, or emitted to fall from a higher energy level to lower energy level, is equal to the difference between the energies of the two energy levels. The fact that an electron to move from one energy level to another absorbs or emits specified amount of energy provides an evidence for the existence of energy levels within an atom. An electron can only reside in a certain area called the energy level by having specified amount of energy. If you lose part of the energy, you fall to a lower energy level. If you absorb extra energy, you jump to higher energy level. So if you are asked, how can you provide an evidence for existence of energy levels within an atom? Tell the examiner that an electron to move from one energy level to another requires specified amount of energy, or absorbs or emits specified amount of energy. So this shows that there are specified energy levels within an atom. When the frequency of radiation emitted by an electron falls within the visible part of the spectrum, then it is seen as a color. Although in chemistry, we don't use the colors like red, blue, yellow. We use lines specified by frequency. In physics, you will know that the radiation is made up of patterns from gamma rays, X-rays, UV light, visible light, infrared, radio waves. So it's only in that small part of the spectrum called the visible part of the spectrum where our eyes can detect the frequencies as colors. But in chemistry, we don't refer them to colors, we refer them as lines. So if the radiation has got a frequency within the visible part of the spectrum, then it will be seen as a line or as a color. Atomic spectrum. Atomic spectrum is a characteristic pattern of radiation is absorbed or emitted by atoms of an element. Each atom produces characteristic pattern of absorbed radiation or emitted radiation. That different patterns can be used to identify an element. Application of atomic spectrum to identify elements by flame tests.
Science Foundation College and Master's with discipline, knowledge and integrity, based on business sciences, the motto we lay our foundation. Let's work together, divided we fall, united we stand, we shall overcome. Let's go for a better utopian future.
B. Advertising lamps. By using different elements in the bulbs, you produce light of definite colors, green, yellow, blue, and so on. And in fireworks, atomic spectrum of hydrogen is categorized as absorption spectrum or emission spectrum. 1. Hydrogen absorption spectrum is observed as dark lines on a black background when white light is shown through hydrogen at low pressure. The dark lines represent absorbed frequencies in the white light for an electron to jump from lower energy level to higher energy level. In order for an electron to jump from lower energy level to higher energy level, it absorbs energy from the white light. The absorbed frequencies are represented by darker lines on the black screen. The hydrogen emission spectrum is observed as a series of lines when electric discharge is passed through hydrogen at low pressure. In each series, the interval between emitted frequencies of lines becomes smaller towards the high frequency or energy side until lines run together to form a continuum of light. For example, Balmer series in the visible part of the spectrum is shown below. The first line is red, the second line is green, the third line is violet. The interval between red and green is bigger than the difference between green and violet, and so on. So towards the high frequency side of the spectrum, the difference between lines keeps on decreasing until continuous light is formed. The emission spectrum of hydrogen is due to radiation is emitted when excited electrons jump from high energy level to lower energy levels. we saw that when an electron jumps from a higher energy level to lower energy level, it emits energy in the form of radiation. When the radiation fall within the visible part of the spectrum, then they are seen as color. So the Balmer series in the hydrogen spectrum is due to radiation caused by electron jumping from a higher energy level to lower energy level and emitting radiation with the frequencies within the visible part of the spectrum.
In this video, we're going to look at absorption and emission line spectra. So we'll start with a quick review of the Bohr model of the atom. The protons and neutrons are located in the nucleus of the atom, and the electrons are located in energy levels or shells around the nucleus. Electrons can only exist at certain energy levels with discrete amounts of energy. So an electron can occupy energy level 1 or energy level 2, but not in between energy level 1 and 2. The next point is that electrons can transition between energy levels. So that means an electron can transition from n equals 1 to n equals 2, or from n equals 3 down to n equals 1. If an electron absorbs a discrete amount of energy, it can transition to a higher energy level, which is called its excited state. So for example, an electron can absorb a discrete or exact amount of energy, and it will transition from an n equals 1 to an n equals 2 energy level. If an electron emits a discrete amount of energy, it can transition to a lower energy level. So for example, an electron in the n equals 2 energy level can emit or give off energy and transition to an n equals 1 energy level. So next we look at how these electron transitions between energy levels give rise to absorption and emission line spectra. So here we have again the Bohr model of the atom, and here we have an electron in the n equals 2 energy level. And these arrows show the electron transitioning to the n equals 3 energy level, the n equals 4 energy level, the n equals 5 energy level, and the n equals 6 energy level. And here we have an absorption spectrum. You may remember this from the previous video. An absorption spectrum has black lines on a colored background. Below our absorption spectrum, we have the energy levels of the atom from n equals 1 to n equals 6. And as you can see, the colored arrows on the diagram, they correspond to the colors that are missing from the absorption spectrum. As we mentioned earlier, electrons can transition between energy levels if they absorb discrete amounts of energy. So if we start with this red arrow here, the electron has transitioned from the n equals 2 to the n equals 3 energy level, and the energy that the electron has absorbed corresponds to the wavelength of red light. Next we'll have a look at this blue arrow here. The electron has transitioned from the n equals 2 to the n equals 5 energy level, and the energy that the electron has absorbed corresponds to the wavelength of blue light. So to summarize, the reason for these black lines on an absorption spectrum is that the electron transitions between n equals 2 to 3, or 2 to 4, or 2 to 5, or 2 to 6. The electrons have absorbed the energy, and the energy that's absorbed corresponds to the wavelength of visible light. So in the previous example, we saw how electrons can transition to higher energy levels when they absorb energy, and the energy that they absorb is related to the wavelength of visible light. One thing you'll notice about this diagram is that the arrows are going in the opposite direction. So these electrons are transitioning from higher energy levels to lower energy levels. And again, each electron transition has its own color. So here we have our emission spectrum, which has colored lines on a black background. So here we have the energy levels within our atom from n equals 1 to n equals 6. So we'll start with this red arrow here. This red arrow represents an electron transition from the n equals 3 to the n equals 2 energy level. When an electron transitions from a higher to a lower energy level, it emits a discrete amount of energy, and the energy that is emitted by the electron corresponds to the wavelength of red light. Next, we'll have a look at this blue arrow here. This blue arrow represents an electron transition from the n equals 5 to the n equals 2 energy level, and when the electron transitions to a lower energy level, it emits energy, and the energy that's emitted by the electron corresponds to the wavelength of blue light. So to summarize, the reason for these colored lines on the black background of an emission spectrum, they correspond to the energy emitted when an electron transitions from a higher energy level to a lower energy level, and in this case the energy level is n equals 2. Next we look at the hydrogen emission spectrum. So here we can see the different types of electromagnetic radiation emitted as electrons transition from higher to lower energy levels. We have UV radiation, visible light, and infrared radiation. So we'll start by looking at electron transitions to n equals 1, which is the ground state, and they correspond to UV radiation. So UV radiation is the highest energy, it has a high frequency, and a short wavelength. Next are electron transitions to n equals 2, and they correspond to visible light. So in visible light, violet is highest energy, red is lowest energy. In addition, violet light has the highest frequency and the shortest wavelength, red light has the lowest frequency and the longest wavelength. And finally, we have electron transitions to n equals 3, and that corresponds to infrared radiation. So infrared radiation is the lowest energy of all three emissions, it's the lowest frequency, and has the longest wavelength.
Relationship between frequency and energy of radiation considered in HF, where H is Plancker's constant equal to 6.625 joules per second, and also frequencies can be expressed as speed of light over the wavelength of light. So we can characterize a radiation in terms of energy, frequency, or wavelength. The different series of lines in a hydrogen spectrum depends on to which energy level the electron is returning. When they are returning to energy level 1 from any other energy levels, then we have the Riemann series, electron return to the first energy level. When they return to the second energy level, it becomes Balmer series, that's third energy level, Pacheni series, fourth energy levels, bracket series, and then to the fifth energy level, Fund series. Electron configuration, the placement of electrons into energy levels of an atom. The rules are: electrons are placed in energy levels of lower energy first. If orbitals have got the same energies, they are first filled singly before pairing begins. Subdivision of main energy levels. The principal quantum numbers designated by 1, 2, 3, 4 dash dash are further subdivided into sub-energy levels designated by SPDF. So, first shell is subdivided, is not divided into 1s. 1 is divided into 1s, 2 is divided into 2s and 2p, 3 is divided into 3s, 3p, 3d, 4 is divided into 4s, 4p, 4d, 4f, 5 is divided into 5s, 5p, 5d, 5f, then 6 is divided into 6s, 6p, 6d, 6f, and similarly 7 is subdivided into 7s, 7p, 7d, and 7f. The order of energy can be obtained from the table as shown. So S has got lower energy level than 2S, than 2P, than 3S, than 3P, than 4S, and so on. S carries the maximum of 2 electrons. P carries the maximum of 6 electrons. D carries a maximum of 10 electrons, and F carries a maximum of 14 electrons. So if you write electronic configuration of an element, say with 20 protons, then we shall put the first 2 electrons and say it is 1s2, the first 2 electrons, 18 electrons remaining, then we shall put the next 2 electrons in 2s, 16 electrons remaining, then we shall put the 6 electrons in 2p6, then we shall put the 2 electrons in 3s2, then 3p6, then 4s2. So an element with 20 electrons, we shall have 1, 4, 10, 4, 10, 12, 18, 20. So you keep on putting electrons, putting the maximum of 2 electrons in S, 6 electrons in P, 10 electrons in D. So an element with the atomic number equal to 20. The first 2 electrons will be in S, those are 2, then another 2 electrons in 2s, those are 4, 6 electrons in P, those are 10, 2 electrons in S, 12, 6 electrons in P, 18, 2 electrons in S, which will be 20. Another element, say with 32 electrons, atomic number 32, we shall put the first 2 electrons there. So 1s2, 2 electrons here, 2s2, 6 electrons there, 2p6, 2 electrons there, 3s2, 2 electrons, 6 electrons is here, 3p6, 2 electrons there, 2 electrons here, 4s2, these are 20, then 3d, 10, from D we go to 4, 4p2. In 4, there are 4 electrons, so this element is in group 4. The outermost shell is 4, so it is in period 4. The outermost filled shell will give you the period, so the outermost filled shell here is 4, so this element is in period 4. The number of electrons in outermost shell is 4, 2 in 4s, 2 in P, so it is in group 4. This element, the outermost filled shell is 4, so it is in period 4. The number of electrons in the outermost shell is 2, so this element is in group 2. Period 4, group 2. The number of electrons in the outermost filled quantum shell gives the group of the element, and the outermost filled shell gives the period of an element. So the number of electrons in the outermost shell, which is the 2, is 5. So 5 is the group of nitrogen. Then 2 is the period in which nitrogen resides. So nitrogen is in period 2 because 2 is the outermost filled shell, and then the outermost filled shell of 2 has got 5 electrons, which is the group in which nitrogen belongs.
Embuze nuno kaba, embuze nuno sinda, tulire nyike, olusosanga kaba, ndi mujabula, waliwo jabalondemu, soma kwalema, osoma tebikyagasa, ddagala lyabula, erya sirimu lyalema, usiru watukwata, ddagala netulyejjako, embuze nuno kaba, embuze nuno sinda, tulire nyike, olusosanga kaba. Tribalism, obutesigangana, obufere, embuze nuno kaba, embuze nuno sinda, tulire nyike, olusosanga kaba, tuline ebbanja, tulina digoba, tulina dita, kikwaso tulitundule. Embuze nuno kaba, embuze nuno sinda, tulire nyike, olusosanga kaba, olabushoni, tribalism, obutesigangana, obufere, embuze nuno kaba, embuze nuno sinda, tulire nyike, olusosanga kaba, embuze nuno kaba, embuze